Hello again. In today's video, we're going to be looking at learning objective number 7. So we're going to be looking at quantum mechanics and quantum numbers. So we're going to be looking at the modern view of an atom. Um, so looking at everything that led up to it and what exactly it is. So quantum mechanics is our modern view of the electrons within an atom. And everything we've talked about so far in this chapter really kind of led up to developing quantum mechanics. So the idea of quantized energy from Planck was there to explain what was going on with the photoelectric effect and line spectra. So Planck came up with the idea of quantized energy. Einstein used that to explain the photoelectric effect, and then line spectrum of hydrogen also used the idea of quantized energy, and it was from Balmer and Rydberg. Okay, so our quantized energy allowed us to explain these two phenomena, and then from these two, Bohr came up with the atomic model of hydrogen. Okay. Then with our atomic model of hydrogen, let's write that, along with the uncertainty principle, and matter waves, these three things were then used to develop quantum mechanics. Which is Erwin Schrödinger. So Erwin Schrödinger a name a lot of people are familiar with because of pop culture. You've probably heard of Schrodinger's cat, or there was that show with some guy named Schrodinger. Anyways, but Erwin Schrödinger was an Austrian physicist, and he developed a mathematical treatment that included both the wave and particle nature of matter. Okay. That mathematical treatment is known as quantum mechanics. Quantum mechanics. And it is how we are currently dealing with subatomic particles that behave as waves. Okay. So quantum mechanics is also known as wave mechanics. And all of these mathematical equations that are in there are there to try and determine information about the energy and location of an electron within that. Which, due to the uncertainty principle, is not an easy thing to do. So these mathematical equations came to be known as Schrodinger's wave equations. And it uses the symbol psi to describe the electron. Okay? So what happens is you treat an electron as a wave. And it's going to travel around the nucleus in a wave or as a wave. So if we think about our nucleus and then our electron around it, so 4 is thought of as just this orbit, so this allowed orbit. That's how it was described in the Bohr model. But taking into account the idea of a wave, you actually take, and it looks more like this, where we have an average distance from our nucleus, but our wave, when it comes back on itself, it has to constructively interfere, so it has to overlap. So it has to have a very specific wavelength associated with it in order to not destructively interfere and cause it to spiral into the nucleus. So this actually described why the electron doesn't spiral into the nucleus and explode. So the electron is traveling in this wave. And this wave has to have a specific wavelength in order to constructively interfere and not destructively interfere. So again, this is how he's able to actually describe why the electron does not spiral into the nucleus, because it has a specific wavelength orbiting around or traveling around the nucleus. So in order for this to occur, we have 2 pi r is equal to n wavelength, where our n is that principal quantum number, so it is an integer. So this n value is 1, 2, 3, 4, and it describes how that works. And if these are not equal to each other, these will be in a non-allowed or forbidden orbit. So if we have 2 pi r equals n wavelength, this is an allowed energy state for the electron. So again, a specific wavelength associated with that. If 2 pi r does not equal n lambda, then there will be destructive interference, which again spiral in the nucleus and explode. So this is a forbidden energy state. So it does not exist. The electron will not go there. Okay. So basically what we do in quantum mechanics is we treat an electron like a standing wave. So here, is treated like a standing wave. So we've got a string that's held in place in 2 spots, here and here. And that string is plucked. And we can have n equals 1, or n equals 2, n equals 3, where we have 0 nodes, n equals 1. So no areas of 0 amplitude. 1 node right here, and n equals 2, and 2 nodes in n equals 3. So anytime that we have a 0-point magnitude, these points right here, that's a node. So our first one we call the fundamental. And then we have the first overtone and the second overtone. And if you've played any string instruments, this will make a little bit more sense. If not, it's okay. We'll describe it a little bit more. So, higher frequencies have more nodes. So as our n value becomes larger, we will have more nodes. Okay? And this is how we generally think about an electron, as a wave. So our wave function that is our set of wave equations that are going to describe the properties of a wave, specifically our electrons acting as waves. So these are our set of wave equations. Okay, so our psi is our electron. If we take our psi squared, this actually provides information about the electron's location when in an allowed energy state. So psi itself is two-dimensional, or one-dimensional. Psi squared brings us in to all three dimensions. So it does not give us the precise location because of the uncertainty principle. But it will give us an approximation of the location. So it gives us the probability of finding an electron within a certain range. So if we're thinking about our atom, we can give a range that electron can be in, or a probability that the electron will be in a specific place in reference to where the atom itself is. And we call this probability, or the psi squared is our probability density. Or electron density. So lots and lots and lots of equations are done in order to determine this probability density. And again, it's based on an electron being in an allowed energy state. So our probability density looks something like this. Okay, so it basically gives you the probability of finding an electron a specific distance away from the nucleus. So this is our 0 point, and it goes from there. So what we're looking at is where there's a high probability of finding the electron versus a low probability of finding an electron. Okay, so high probability will have a large chi-squared value. And then if we have a low probability, we'll have a small chi-squared value. Okay. From this information, this probability density, the physicists, including Schrodinger, came up with the idea of orbitals. Or orbitals are our visual representation of the probability density. So it's basically our x, y, and z axes, and every time you solve for Schrodinger equation or wave function, you get something like this. A little dot, 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 hundreds and millions of times, and this is our spatial distribution in 3 dimensions in 3D of the electron density. Okay, so each orbital that we're going to look at has its own characteristic shape and energy. And orbitals themselves are described by quantum numbers. And these quantum numbers come from solving for the Schrodinger equations. Also, each orbital has a unique set of 3 quantum numbers. So, basically we're visualizing the electron cloud here. So the orbitals is visualizing the electron cloud. So it doesn't say how the electron moves because of the uncertainty principle. It just says, okay, out of the 5 billion times we looked, it's most likely to be here, less likely to be here. And our orbitals, that visual representation, is basically 90% chance of finding the location within these boundaries. That does not mean they can't be found outside. They can be found very far away, but this is where they're most likely to be found. So our quantum numbers. Of course, we have our n value, our principal quantum number. This is still a thing within quantum mechanics. Our principal quantum number describes our energy level and kind of reference away, distance away from the nucleus. But we have additional quantum numbers we're going to look at. We have L, and we have m sub L. We'll look at another one as well. But all three of these are used to describe the electron, where our L is called the angular quantum number. And m sub L is called the magnetic. Okay. So our principal quantum number, that's any integer value. So this can be n equal 1 to infinity. And it's going to describe the energy of the orbital. Okay. The angular quantum number, our m sub L, can have values anywhere between 0 and minus 1. And this is going to describe the shape of the orbital. So our, or did I say m sub L? Sorry, this is L value. Our L values can be 0, 1, 2, 3, so on and so forth. And we're going to have letters that are used to describe them, where 0 is described by the letter S, 1 is described by the letter P, 2 is described by the letter D, and 3 is described by the letter F. where our S describes a spherical shape, our P is a dumbbell shape, our D is a clover shape, and our F is complex, almost like a flower in some cases. Just very interesting. Now, after we're looking at our angular quantum number and our principal quantum number, our last one is our magnetic quantum number. That's our m sub L. And it can equal values anywhere between negative L to positive L. This is going to describe the orientation in space. So it's kind of like our X, Y, and Z. So a sphere doesn't have any specific orientation. Anywhere you turn it, it's still going to look like a sphere. So if we have an S orbital, it will only have one orientation. But if we have something like P, it will have 3 possible orientations. D will have 5 possible orientations, and F will have 7 possible orientations. Next thing we want to look at are shells and subshells. And bring into the idea, so these are just vocabulary words that we're going to use our quantum numbers for. So we've got our shell. This is orbitals with the same n value. And the shell is described by that n value. So n equals 1, 2, 3, so on and so forth. And then within each shell, we're going to have subshells, which are described by different orbital types. So these are our different orbital types within a shell. And then within subshells, we have individual orbitals. So these are within subshells. And they are the actual locations of our electrons. Okay, and each orbital can hold a maximum of 2 electrons. Once all of the information is known about our shells, subshells, and our orbitals, we can actually look at our visual representation of our orbitals. So here is what the visual representation would look like. Our first one is our s orbital. And it only has one orientation, so we only see just the one. So it would be a s subshell, and in the s subshell, there is just the one s orbital. So only one orientation for a sphere. Within our p subshell, we have three possible orientations along our x, y, and z axes. So we have three p orbitals. We have a px, where our lobes of our p orbital are along the x-axis. We have a pz, where we're along the z-axis, and then a py, where we are along the y-axis. So remembering x and y are generally what we normally think of. Well, let's actually write it the way that's shown here. We have an x here, a z here, and then behind and in front of this flat plane is our y-axis. Okay, with our D subshell, we have 5 possible orientations for the 4 lobes of our D orbital. And we have a dxy, where our lobes are on the xy axis, dxz, where we're along the xz axis, a z squared, where all of it is along just the z axis, a dyz, where we're along the yz axis, and then dx squared minus y squared, where we're actually in between the x and y axes. And then lastly, our f subshell. Here, we've got just a plethora of different ones, and there are 6 lobes in total for most of these, and they've got some really funky orientations along some really weird axes. So just know that if you have a s subshell, you have 1 s orbital. If you have a p subshell, you have 3 p orbitals, and those 3 p orbitals are described by which axes they're on. Same thing with our d subshell. If we have our d subshell, we have 5 possible d orbitals, and their names or orientations are based upon which area the lobes are in. Our f subshell, there are a total of 7 f orbitals within the f subshell, and they're just crazy in shape. But we just usually, with s, we're thinking spherical, with p, we're thinking dumbbell, d is a clover, and then f is kind of like a flower. So when we think about our possible values of our quantum numbers, we usually arrange it by our principal quantum number. So we have n, and within n, we have different possible levels or possible values of L. Then we have a subshell designation, what we call that subshell. Then we have possible m sub L values. And then number of orbitals. In subshell. And lastly, our total number of orbitals in the shell. Let me just move this a little bit. Okay. And so we have n equals 1, n equals 2, n equals 3. And n equals 4. So thinking about our L values, L can be anywhere between 0 and n minus 1. So if n equals 1, and minus 1 is 0, so our only possible option for L is 0. If we have an L that is 0, we're talking about an S subshell. So our subshell designation here would be 1, which represents our N value, and then S represents our L value. Emps of L value are possible. Emps of L values are between negative L and positive L. The only L value we have is 0, so our Emps of 0 or Emps of L is 0. So we only have one orbital because we only have one orientation. And that means we only have one orbital in the total shell. If we're talking about n equals 2, our L values are between 0 and n minus 1. N minus 1 is 1, so we get 0 and 1. If we're talking about L being 0, our subshell is S, so we have a 2S. If our L is 1, our subshell is P, so we get 2P. With 2S, our possible L values are just 0. And then with our 2P, our L value is 1, so we can be 1, 0, and minus 1. So there's our 3 orientations. So 1 orbital, because we have 1 orientation for 2S. 3 orbitals, because we have 3 orientations for 2P. If we add these two together, our 1 orbital from 2s subshell, our 3 orbitals from 2p subshell, we get a total of 4 orbitals in the shell. Moving on to 3, our possible values for L are 0 to n minus 1. N minus 1 is 2, so we have 0, 1, and 2. With a 0, it's an S, so we get 3s. With a 1, it's a P, 3p, 2, it's a D, 3D. We then move on to our possible L values. If we have or Emps of L values, if we have an L that's 0, our only possible Emps of L is 0. L that's 1, we have 1, 0, minus 1. And then with 2, we have 2, 1, 0, minus 1, and minus 2. 1 here, 3 here. Now we have 5 possible orientations for our 3D. So we put a 5 there. Adding all these together, 5 plus 3 plus 1 gives us 9 total orbitals. And lastly, with an n equals 4, we have all the way up to n minus 1, which would give us 3. So we have 0, 1, 2, and 3. So we have 4s, 4p, 4d, and then that 3 is an f, so 4f. 0, 1, 0, negative 1, 2, 1, 0, negative 1, negative 2. Now we're between 3 and negative 3 for our 4f. So those are our 7 possible orientations. So we have 1, 3, 5, and 7, giving us a grand total of 16 orbitals within our n equals 4 shell. Now, if we look back up here, we see that we have 1 possible orientation for our S, which is 0. So this would be our 0. We have 3 for our P, so this could be 1, 0, minus 1. We have 3 or 5 for our D. So this could be 2, 1, 0, minus 1, minus 2. And then 7 for our F. 3, 2, 1, 0, minus 1, minus 2, minus 3. So those are all our orientations for our orbitals right there. Okay? So it's pretty easy to solve for the quantum numbers of any orbital within there, but we are also going to have some things to think about when we're doing this, making sure that we don't start seeing P until we get to n equals 2. We don't start seeing D until we get to n equals 3. We do not start seeing F until n equals 4. So in our very first subshell, we have S, and in our very first shell, we have S, and every subsequent shell has S. But we increase our number of subshells, or different types of subshells, as we go from n equals 1 all the way to n equals 4, and so on. We can use the periodic table as kind of a guide for this. So if we look at our periodic table, we can actually very easily give designations to everything within the periodic table. So basically, when we're looking at this, if we look at an atom, we can determine what electrons, or where the electrons are, the outermost electrons, what subshell they're in. So this would be 1s, 2s, 3s, so on and so forth. 4s, 5s, 6s, sorry, and then 7s. And we can start up here. We see that in our P block, so this is our S block. Next, we move on to our P block. In our P block, we start out with 2. So we have 2p, 3p, 4p, 5p, 6p, 7p. And then right here is our D block. And with D, we start at 3. So 3D, 4D, 5D, 6D. And then down here is our F block. F starts at 4, 4F, 5F. We'll be using this idea in a further lecture when we start talking about electron configurations. So write this down for now, and I will revisit this very soon. Okay, so last part of this, let's do an example. How many subshells are in the third shell of an atom? And we want to label the subshells. And then, how many orbitals are there? Lastly, maximum number of electrons. In the third subshell. Okay, so first, if we look at our third subshell, that's this one right here. N equals 3 is our third shell, excuse me. If we look at our third shell, we see that we have 1, 2, 3 possible subshells. So in the third shell, there are 3 subshells. Their subshells are 3s, 3p, and 3d. Wants to know how many orbitals there are in the third shell. So again, we look up here. We see that in our 3s subshell, there's 1 orbital. In our 3p, there's 3. In our 3d, there's 5, giving us a total of 9 orbitals. And then maximum number of electrons. Hopefully you remember from earlier that each orbital can hold a maximum of 2 electrons. So if we have 9 orbitals, we multiply that by 2, we have 18 maximum electrons. Okay, that's everything for this video and this learning objective. I will see you guys in the next one.